All right, in this next segment of the chapter, we're going to talk about a little bit more about one more important colligative property that is actually quite important in medicine and biology, and you'll do some fun problems in the homework on this, and also talk a little bit more about non-homogeneous solutions. We'll just talk a little bit about it. We won't really cover too many quantitative topics, but it's useful to know about them. Okay, so in this lecture, we're going to define osmosis and explain the source of osmotic pressure, calculate osmotic pressures given concentrations, and define and give examples of colloids. Right. So osmosis is the flow of a solvent from a solution of low concentration into a solution of high concentration. And the solutions may be separated, usually are separated by a semi-permeable membrane. And the reason why it needs to be semi-permeable is it allows the solvent, but not the solute, to flow through it. So if there wasn't a membrane, then if you have a low concentration to high concentration, the solute would just move along with the solvent, and everything would equalize out. But if the membrane is semi-permeable, then only the solvent can go through. The solute can't. And so what you see is you're going to have equalization to have better mixing. Things are going to become more uniform. And since the solute can't move to make things more uniform, right, there's excess solute here, not enough solute here, the solvent has to move to make things more uniform. And so you get changing volumes. You get solvent moving from one side to the other of the permeable membrane. And this is very important. It happens a lot in biology, where you have cell walls as semi-permeable membranes. There's a number of applications in chemical engineering separations as well. So the amount of pressure that is needed to keep osmotic flow from taking place is called the osmotic pressure. So you can imagine you could either let the solvent change, or you could, the lower, if we go back a little, you could either have the concentrated solution and let the solvent. You could either let the more concentrated side of the solution rise, or you could apply pressure to it and forcing the liquid back down, and that would cancel out the effect of the solvent moving over. And so the pressure you need in order to do this, to keep the osmotic flow from taking place, is called osmotic pressure. So you could you can envision the force of this, the solvent pushing against the membrane, pushing through the membrane in order to get to the other side, as essentially an equivalent pressure. And so the osmotic pressure, which is usually expressed as a capital pi, is directly proportional to the molarity of the solute particles. So you can calculate the osmotic pressure by the concentration of the solute times R times T. Now you might say, wait, solute molarity? I thought we were talking about colligative properties, where we're interested in the concentration of the solvent. So the concentration of the solvent that's important, isn't it, right? So it turns out that's true. The more accurate equation looks like this, that the osmotic pressure equals minus RT divided by the molar volume of the solvent times logarithm of 1 minus the mole fraction of the solvent. But if that obviously is a function of the solvent, but when the mole fraction is almost 1, then it turns out reduces to the standard osmotic pressure equation. So as long as the concentrations are relatively low, 1 or 2 molar or lower, then this simple equation ends up working just great, and you just have to monitor the concentration of the solute. And notice now it's in molarity, not molality. Monitor the concentration of the solute instead of the concentration of the solvent. So this is sort of the true equation, but this is the one that we use since it's applicable in almost all circumstances that you generally run across. Because generally, if you're dealing with aqueous solutions, you're usually dealing with relatively low concentrations of solutes. So this is what an osmotic cell would look like. And so if you start out with a bunch of solute here and just solvent here, then of course the solvent is going to go over onto this side. But if you have it set up like this, eventually it'll reach equilibrium, and because you do have pressure on the other side. If you have excess fluid, if you look at the difference in levels between this and this, then you can, that'll actually be equal to a pressure. And so this is how you can actually measure concentration this way. You can set up a cell like this, watch to see what the water level difference is, calculate the pressure due to that, and from that back calculate out what the concentration of your solute here was initially. So one other factor in all these colligative quantities to consider is what's called the Van Hoff factor. So if you dissolve sodium chloride in water, you're not actually creating 1 mole of solute, you're creating 2 moles of solute, the sodium and the chloride. If you have magnesium chloride, well, you're generating 3 moles of solute. So that, to the first approximation, that's relatively accurate. It turns out that in a solution that it turns out that you don't always get quite as many as you thought you would. There's a theoretical Van Hoff factor is the ratio of moles of solute particles to the moles of formula units dissolved. But it's generally less than theoretical due to ion pairing in solution. Although the ions are surrounded by water, they don't always entirely move away. They have a tendency to like cluster next to each other. And so the measured Van Hoff factor often causes the delta T to be smaller than one might expect. Again, the Van Hoff factor is if you put in 1 mole of sodium chloride, you get 2 moles of ions. So the theoretical Van Hoff factor is 2. In practice, maybe it's 1.8 or 1.9. In fact, sodium chloride, it's 1.9. The sodium chloride is almost entirely disassociated, but you have a lot of ion pairing. They tend to clump up a little bit more. Whereas if you get to something like magnesium chloride, the I would be 3, then you'd get a 2.7. And this Van Hoff factor, this occurs, of course, in freezing point elevation as well. Magnesium chloride is actually quite good at as an ice melt. It's quite powerful as an ice melt because for each you're releasing a lot of sodium chloride, you're releasing a lot of ions per mole. Magnesium chloride is also extremely corrosive, so you don't actually use it that much, even though it lowers boiling point by quite a lot, because it releases 3 ions. It's just too corrosive to use generally. So again, colligative properties are very important in biology and medicine. If you put a normal red blood cell in an isoosmotic solution that has the same concentration of water inside the cell and outside the cell, then it has the nice little indented disc shape like it's supposed to. But if you put it in a solution that has too much salt, then you get it deforms in a weird way. And if you put it in a solution that has in pure water, then the water flows into the cell and it swells up and it bursts. And this is why it's actually deadly to put someone on an IV solution that's pure water. You're going to mess up the concentration of water in the blood, and you'll have all your cells will be swelling because the blood will be too dilute. And that's why you need saline solutions. That saline solutions is balanced to be isoosmotic.